Most people will never stand next to the machines that keep oil moving, cities supplied, and chemical plants running. When one of these pumps fails, pressure drops, production stops, and entire systems can begin to shut down. Some are built for clean water, some for crude oil, and some for chemicals that can destroy the wrong metal in days. Before they ever reach a pipeline or plant, they are cast, machined, balanced, sealed, and tested to exact standards. This is how industrial pumps are built for oil, water, and chemicals. Most industrial pumps are never seen because they spend their lives behind walls, inside plants, and beneath factory floors. Their purpose sounds simple: move liquid from one place to another and keep it moving without interruption. But the liquid may be drinking water, crude oil, wastewater, solvent, acid, slurry, or chemicals hot enough to burn. Each of those fluids behaves differently, which means the pump must be designed around pressure, temperature, corrosion, and flow. In a city water system, pumps help maintain the pressure needed to reach homes, hospitals, and fire hydrants. In an oil pipeline, they keep crude moving over long distances where stoppages can disrupt storage, transport, and refining. In a chemical plant, a leaking pump can mean contamination, lost production, fire risk, or a full emergency shutdown. That is why an industrial pump is never treated as just another rotating machine on a concrete floor. Some are built for enormous flow, moving thousands of gallons each minute, while others are built for extreme pressure. Most industrial pumps fall into two main families: centrifugal pumps and positive displacement pumps, each built for different duties. However different they look, the job stays the same: keep a larger system alive by keeping fluid under control. And before any pump can be trusted in the field, it has to be designed and built with precision. Before a single piece of metal is cut, an industrial pump exists entirely as a set of mathematical problems. Engineers must first know exactly what the machine will face in the real world. They calculate the required flow rate, the pressure needed to push the fluid, and the exact temperature it will run at. They also have to account for the fluid itself, because pumping clean water is completely different from pumping thick, abrasive crude oil. Using advanced software, they create digital models of the pump's internal geometry. This allows them to simulate how the liquid will behave as it hits the spinning blades of the impeller. They look for turbulence, dead zones, or areas where the pressure might drop too low and cause destructive bubbles to form. Once the shape is proven in the computer, the next critical decision is what to build it out of. Cast iron might be fine for a municipal water pump, but it would dissolve quickly in a chemical plant. For harsh environments, engineers specify stainless steel, bronze, or even exotic nickel alloys that can withstand concentrated acids. Every dimension and material choice is governed by strict industry codes, like the standards set by the American Petroleum Institute. These rules ensure that a pump handling flammable oil will not crack under pressure or spark a catastrophic fire. Only when the design is locked, tested digitally, and fully documented does the manufacturing process actually begin. And that process starts in one of the oldest and most unforgiving environments in heavy industry, the foundry. In the foundry, the pump begins not as a machine, but as a hollow shape waiting to be filled with molten metal. Large components like the casing and impeller are usually made by casting, a process built around heat, gravity, and timing. First, workers create a pattern of the part, shaping the exact form the finished metal will eventually take. That pattern is pressed into specially prepared sand, leaving behind a cavity that becomes the mold. For internal passages, separate sand cores are placed inside, so the liquid pathways already exist before the metal is poured. Once the mold is closed and secured, molten iron or steel arrives at temperatures hot enough to light the inside of the mold. The pour has to be steady, because trapped air, uneven cooling, or turbulence can leave defects hidden deep inside the casting. After the metal cools, the sand mold is broken apart, and the rough pump component finally appears for the first time. It is still unfinished, covered in scale, excess metal, and the scars of the casting process. Workers cut away the gates and risers, then clean the surface so inspectors can begin looking for flaws. Some defects are visible immediately, but others are hidden inside the metal and must be found with X-rays, ultrasound, or dye testing. If the casting passes, it can move forward. If it fails, the part is rejected before any more work is wasted on it. What leaves the foundry is no longer liquid metal, but it is still far from being a precision machine. The next stage is where rough castings are turned into exact mechanical parts that can actually run. In the machine shop, the rough casting stops being a shape and starts becoming a precision component. The surfaces that matter most are the ones nobody will ever see once the pump is assembled. Large casings are mounted on heavy boring mills, where cutting tools remove metal in slow, controlled passes. Every internal bore must be round, straight, and sized to a tolerance measured in thousandths of an inch. The suction and discharge flanges are machined flat, so the pump can seal properly against the piping it will serve. Bearing housing bores are cut with even tighter accuracy, because a small misalignment can shorten bearing life dramatically. At the same time, the shaft is manufactured from solid bar stock, often stainless steel for corrosive service. It is rough-turned, sometimes heat-treated, then finished to precise diameters where bearings and seals will sit. The shaft must run true, because even a tiny amount of runout will create vibration once the pump reaches full speed. The impeller receives its own machining, with the eye bore, hub, and wear ring surfaces cut to specification. Then, it is placed on a balancing machine and spun, so technicians can find any uneven distribution of mass. Small amounts of metal are removed until the impeller can rotate smoothly without shaking the entire assembly. In some pumps, the internal flow passages are polished, reducing friction and slightly improving hydraulic efficiency. By the time these parts leave the machine shop, they are no longer castings, but finished mechanical components ready to fit together. One of the most critical parts of the entire pump is also one of the smallest and easiest to overlook. It is the mechanical seal, the component that prevents fluid from leaking out where the shaft exits the casing. Without it, a water pump loses efficiency, an oil pump can become a fire hazard, and a chemical pump can release something toxic. The seal works by pressing two extremely flat faces together, one rotating with the shaft and one held stationary. Between those two faces is a microscopic fluid film, thin enough to limit leakage but thick enough to provide lubrication. That balance is delicate, and if it is lost, heat rises quickly and the seal can fail in a very short time. For ordinary water service, one seal arrangement may be enough, but hazardous fluids often require double seals and barrier systems. The materials matter just as much as the design, because the wrong seal faces will wear, crack, or react with the fluid. Silicon carbide is used where abrasion is severe, while carbon and ceramic combinations are common in less aggressive service. Technicians handle these parts carefully, because the polished seal faces are so precise that a small scratch can ruin them. A pump may be large enough to move thousands of gallons a minute, but it still depends on a seal measured in microns. That is why so many pump failures begin with a component most people will never notice until something starts leaking. Now the finished parts begin to come together, but not like simple bolt-together pieces. First, the bearings are mounted on the shaft, usually heated so they slide into place with an interference fit. Once the bearings cool, they are checked for smooth rotation, because anything that feels rough here will fail in service. The mechanical seal is then installed around the shaft, with its faces carefully cleaned and set. Technicians remove the shipping clips only when the seal is properly positioned, so the delicate faces stay perfect. The impeller is fitted onto the shaft next, and the clearance between it and the casing wear rings is measured carefully. If that gap lies outside specification, the performance of the entire pump suffers. The shaft assembly is then lifted and lowered into the bottom half of the pump casing. Workers carefully align everything before the top casing half is placed and the bolts are hand-started. Bolts are tightened in a specific cross-pattern sequence, so the casing joint seats evenly without distortion. Once torqued to spec, the shaft is turned by hand to confirm everything rotates freely inside. Finally, the coupling is fitted to the shaft end, ready to connect to the motor or engine that will drive the pump. What started as rough castings and loose components is now a complete machine, but it is not trusted yet, not until it proves itself under test. Before any industrial pump can leave the factory, it has to prove that it can do the job it was built for. It is connected to a test loop where engineers can measure flow, pressure, power use, vibration, and seal performance. As the pump runs, valves in the loop are adjusted to move it through different operating conditions. At each point, technicians compare the real performance against the pump's design curve. They check whether it delivers the required flow, whether the head is correct, and whether the efficiency stays within tolerance. Then comes the mechanical run test, where the pump operates long enough for heat, vibration, and alignment problems to reveal themselves. Temperature sensors watch the bearings closely, because rising heat can signal trouble before damage becomes visible. Vibration is measured at multiple points, since excessive movement can shorten seal life, damage bearings, and crack components over time. For some pumps, engineers also run suction tests to determine how close the machine can operate to cavitation. If pressure falls too low at the inlet, vapor bubbles collapse inside the pump and begin eating away at the impeller. Finally, the casing itself is hydrostatically tested at pressure above its normal operating limit to confirm its structural integrity. If the pump leaks, vibrates too much, or misses its performance targets, it does not ship. Only when the data confirms that the machine is stable, sealed, and hydraulically correct is it considered ready for service. Once these pumps leave the factory, most of them disappear into places the public almost never sees. Some are installed in municipal water systems, where they help move clean water toward homes, schools, and hospitals every hour of the day. Others are sent to oil fields, refineries, and pipeline stations, where they keep heavy fluids moving through long industrial networks. In chemical plants, they are trusted with corrosive liquids that can damage equipment quickly if the wrong pump is chosen. Some work inside power stations, moving cooling water, boiler feed water, or other critical process fluids that cannot stop without consequences. No matter where they go, these machines only matter because people continue to inspect them, align them, rebuild them, and keep them alive. Behind every reliable pump is a long chain of workers, from foundry crews and machinists to seal technicians, test engineers, and field service teams. Most people will never see that work, even though modern industry depends on it every single day. And that is often how the most important machines in the world survive, quietly, far from view, doing their job without recognition. If you enjoy seeing how hidden industrial systems are really built, subscribe and stay with us.